Now we know everybody likes photos, so in this section, we're going to have some fun with pictures as a way to recommend other businesses. Our hypothesis for this section is that similar photos get updated for similar businesses. Now, our goal is to enable users to select an image they like, then show them businesses with similar images. The idea is to create sort of a photo-based recommendation. Now, we've taken the liberty ahead of time to tag photos, about 30,000 photos, within Yelp reviews using the Google Cloud Vision API. In this section, we'll need to first identify photos that are similar based on those tags and then group them. The Jacquard similarity algorithm is often used to find recommendations for similar items, as well as part of predicting links. Jacquard provides a measure of similarity between sets, which could be, the set could be two nodes and their attributes. It could be other types of sets as well. Mathematically, it's defined as the size of the intersection divided by the size of the union of two sets. So basically looking at the overlap and then dividing that by the items, the sum of the two items, not counting the overlap twice. So looking at Jacquard a little closer, for example, if we have two sets, one set A containing 4 items and one set B containing 3 items, we're going to first look at the intersection of those two. Which items are the same in both sets? And here we can see orange and banana, so we have 2 items. So the intersection between those is 2. We're then going to look at the union, and that looks at what is the sum of these 2 sets, but as I said, not double counting the intersection. And all that does really is keeps us, this little part here, subtracting the intersection, keeps us from double counting this gray area. So we don't want to count orange and banana twice. So really the union of those two would be orange, banana, cherry, pineapple, and apple, which is 5, because we don't want to double count those, the intersection, the items in both. So Jacquard basically divides the intersection by the union. We have 2 divided by 5, which gives us a 0.4 coefficient. Now, if this sounds familiar, it's probably because there's actually a lot of similarity between overlap and Jacquard similarity algorithms. They both start off with the intersection of 2 sets, but Jacquard looks at the union of those 2 sets for the division, whereas overlap divides by the minimum of those 2 sets. We can kind of visualize why Jacquard is widely used for similarities in general, and overlap is very well suited to finding subgroups and developing hierarchies. The label propagation algorithm is a great choice for grouping, quickly grouping at scale. In this algorithm, the nodes select their group based on direct neighbors using the node labels, taking on those node labels. And the idea here is really that a single label can become dominant in a densely connected group of nodes, but it's less likely or will have trouble crossing sparsely connected regions. With label propagation, it's quite well suited for groups that are less clear, where we have less information, and in particular where we can use weights or seed data to help determine which community a node may be placed in. If we add weights to relationships, we'll do that there at the top, we can see how that may actually change groupings. So there's a lot we can do to use weights and to use seeds to help our algorithm learn. In Neo4j, we use the poll or voting mechanism for label propagation. Now, it initializes first with every node having a unique label if you're doing unsupervised learning. But since label propagation also lends itself really well to semi-supervised learning, we can use seeds, a seed process for pre-assigning node labels that we know are predictive. In this example, we started with 2 nodes having an A label, and then leaving all other ones unique. We're also going to default the node value to 1 so that we can concentrate on relationship values, but label propagation does lend itself to looking at both node values and relationship values. Now, the node values, or the nodes are processed in a shuffled order, or they're shuffled and then processed, and each node acquires the label of its neighbor based on the maximum weight of, in this case, a relationship, or relationship and node if you're using node value as well. Now, this first iteration, we started by looking at or using A, B, and C nodes, and looking at its neighbors, we can see why A, looking at 1, 5, and 2, 5 being the highest value, would acquire an F label. B becomes D in this case. C, looking at the values of 1, 5, 4, and 6, would obviously take 6 and acquire an A value. Now, the maximum weight is calculated based on the weight of its neighbors, the relationship in the node, as I said, and if there are ties, the ties are broken uniformly and randomly. Now, there will be times when a label is not updated because the neighbor with the maximum weight actually has the same label, and that's what we've shown here. In this case, F stayed F because the highest weighted relationship was with a node with a label of the same item. And this is how the solutions begin to converge. Iterations will continue until each node has the majority label of its neighbor, or you've reached a max iteration limit. Now, the max iteration limit prevents an endless cycle where an algorithm can't actually converge in the solution and gets caught in a flip-flop cycle between different labels. Now, in contrast to other algorithms, label propagation can return different community structures when run multiple times on the same graph. This is because, one, the order in which label propagation evaluates nodes can have an influence on the final community structure. And we saw this at the beginning when we said nodes are shuffled and then processed. So shuffling a second, a fourth, an eighth time, you might have a different start process, but also because we have random tie breaking, as we talked about. Now, this is less likely to happen, the different results, in a well-delineated group, but we can also narrow that range of solutions by giving some nodes a preliminary labels, those seed labels, while leaving other ones unlabeled. Unlabeled nodes are more likely to adopt those preliminary seed labels. By the end of the section, we'll have added a way to recommend similar businesses based on the user picture preference. You should also be able to explain the basic differences between Jaccard similarity and overlap similarity, and be able to understand how weights are used to assign labels for label propagation and why seed labels are sometimes used.